This video covers the concept of applying reduction for solving many-to-one type data parallel applications. Recollect that we have already covered data parallel applications in which a set of data is logically subdivided between multiple threads, and for each one of these entries, the thread computes from the inputs, appropriately applies an output. So for each one of the inputs, there is a corresponding output that is generated, and this is a very typical data parallel application. And we've seen how to compute like a simple starting index and ending index for each thread, and running a for loop that iterates over the range for a given thread to process the inputs and generate the corresponding outputs. Remember that the outputs are pre-allocated, so we are not adding entries to this vector fact list. Instead, we are just updating the corresponding entries, and that is important to keep in mind that this list is pre-allocated, so it's important to pre-allocate it. Now let's look at a slightly different problem. In this case, it's a many-to-one problem. Notice that in this example, a number of inputs are supplied in the vector, input vector. There's a number of inputs supplied, and the method essentially returns a single value, right? Notice the difference between here. In the previous approach, we had inputs and outputs, and for each input, there was a corresponding output being generated in the previous example, right? Versus in this case, we have an input vector, a list of values, but we are generating a single output from that list. That means a count. In this case, it is basically counting the number of even numbers in a given vector. So it's iterating over each value in that vector, and the value is even. It adds to the count and returns a count. So you have many numbers, n numbers, but you get one output from it. So contrast this. This one, you had n inputs, you get n outputs. Versus here, you have n inputs, you get one. That means you have many-to-one problem. Let's see how to solve this problem using an approach called reduction. So think about how you parallelize this is with reduction. So let's do an overview starting with a picture. Same, we are given a number list where there's a list of numbers in that list. We are going to do the same data parallel approach where we are going to logically subdivide the numbers to be processed by different threads. Here we have k threads, so we have n numbers and k threads, and we're going to have k threads to process them. And we are going to compute, similar to the previous case, we're going to compute like a start index and end index and have the threads iterate over those subset of numbers. Same idea. However, what we're going to do is we are going to create a temporary intermediate list of results for each one of these threads to update. So what happens is each thread basically computes its own results from its subset of lists and stores it in this temporary value. Yeah, so each thread works on an independent sublist and updates an independent counter. So no two threads will update the same counter. Consequently, race conditions will not occur. Yeah, that's important to keep in mind. That means thread 0 updates index 0, thread 1 will update index 1. It will not update any other index. That means we are going to write the code that way, so it will not update the index. And consequently, race conditions cannot occur. And then the main thread then goes, and finally, once all of the threads are joined, the main thread takes this small list of values and computes the overall result from all of the threads. And this operation, where you're taking a large number of values, possibly it could be millions of them, and reducing it down to a few values. So think about this, you might have a million numbers, but only maybe 100 threads. So you're reducing substantially, making the problem substantially smaller. And this idea is called reduction. And this is a very commonly used data parallel approach for solving problems. Keep in mind, in this one, we don't need any synchronization. This is important to keep in mind. We don't need synchronization because each thread updates an independent location all for itself. So no two threads share the same location. Consequently, no synchronization is required, and hence the solution is going to be pretty good. Let's look at how to implement that picture into code. So we're going to create a method. Here we're going to make an assumption about the number of threads. this assumption is just to keep this example simple. Normally, you will use the number of threads from that are set by default for OpenMP. Here we're going to pre-allocate that counts array. Remember, this counts array is that intermediate. This counts array is that intermediate array to temporarily create. So for each thread, we're going to create that location. So here, that's what the max thread parameter does. So you're calling the constructor for an integer vector and creating 8 entries. So you're calling the constructor to create the object counts with this k entries. In this example, k will be equal to 8. That's what we've set up. And also keep in mind, when the number of threads are not fixed like here, you should think about using that barrier-based approach to create this vector like it was discussed in a previous presentation. So it's important to keep in mind. So keep in mind, when the number of threads are not fixed like this, use that barrier-based approach discussed earlier. Then we're going to do the same data parallel version. We're going to create a parallel section with those shared vectors and the counts. So the input vector and that intermediate are both shared by all of the threads. And then we're going to the same process to compute the start index, end index by evenly dividing. And of course, this one also tries to handle some edge conditions here. And then you run the standard for loop from the start index to end index. And if any value is there, notice how each thread updates that temporary intermediate counts array that was created based on its thread ID. Remember, every thread gets its own thread ID, so no two threads can have the same thread ID. So no two threads will update the same counts. Consequently, race conditions do not occur. Okay? And then once all of the threads are joined, remember this is where the join happens corresponding to the parallel block. Once all the threads are joined, the main thread runs through this counts vector and adds them all up by calling the std_accumulate method and gets the total value and returns the total. And this total will be exactly and should be exactly the same as the serial version, except here most of the reduction operation is done by using multiple threads in that parallel block, thereby accelerating the solution. And this is the parallel implementation that uses the idea of reduction. That reduction approach works pretty well in solving the problem. However, it has a very, very significant hidden performance issue, particularly in the area of caching. And this issue is called false sharing, and we are going to take a slightly deeper dive into false sharing to understand why it is a performance issue. Remember, with this parallelization that we have done, we are using the shared counts array that we are constantly updating. So this one line of code is constantly changing a value in an array, which negatively impacts caching. And we are going to start trying to understand why this is the case. In order to understand this issue, it's important to recollect that caches store copies of data in memory. Remember, we have tiers of caches, and every tier, may it be L3, L2, or L1 cache, is storing copies of the values in RAM. And caches are updated in blocks, like L1 cache size might be like 64 bytes. So anytime a single byte is updated, those 64 bytes at a time have to be updated, stored, or moved back and forth. And this is done to increase cache bandwidth and reduce memory latency. So when you have the shared array in memory, remember that this copies of the shared array is stored on all of these caches in those cache lines. Could be L1 cache, L2 cache, wherever. Whatever is this array that we are using, the shared array, copies of that are stored on the different CPU caches. And these are physically different caches because they are physical hardware. So they are stored physically in different places. Okay. Now the problem is, or the idea of this cache hardware is that the job of the cache hardware is to keep all of the copies coherent and consistent. So that means if one value changes, the corresponding copy in the other part of the cache also has to be updated. This thread may not be using this entry, but the job of the cache, the way the cache is designed, this is the job of the hardware. It's like asking why water is wet. Water is wet. Same way here, the cache entry needs to be updated so that same way, if this value is updated, the same corresponding value in every cache has to be consistently updated. That is how the cache hardware works. So this cache coherence, in order to make sure all of the cache lines in the different CPUs or different cores are all coherent, it requires stalling the pipeline while the copies in the different caches are updated. And of course, stalling this pipeline impacts performance. So this scenario where independent values are used by the threads, but when a thread updates this counter, its copies in other caches also have to be updated, and it makes it appear as if the threads are sharing values, but they aren't sharing any values. They're all supposed to be independent values. There are no race conditions here, so they are independent values. Because it appears as if the threads are sharing values, this scenario is called false sharing. Yeah, and false sharing impacts performance. So that means when this one cache line is updated, the corresponding the copy in another cache line, and the more threads you use, the more cores you use, this issue becomes more and more pronounced because many more copies have to be updated. Same thing happens with the second thread. If this thread updates this value, correspondingly, this value has to be updated in every cache line. So think about it. Each time the thread updates the value, this one cache line has to be updated. Then the next cache line has to be updated. Then this keeps on happening, and this significantly impacts the performance of the program. And this is a significant issue with fault sharing. We can minimize the issue of false sharing by simply using a thread local temporary variable. It's a very simple solution. When you look at the code, it'll be relatively straightforward. So here, all the code is almost the same, except what we've done is we have added an extra temporary local variable. Remember, this is a local variable that is stored on the thread stack. This is not shared between different threads. Each thread gets its own local counter variable that's initialized to 0. And rather than updating this counts or thread ID every time, we simply update the local variable. Since the local variable is stored on independent stacks of the different threads, they do not share the same cache line. Consequently, false sharing does not happen, because usually threads have about a megabyte of stack. So they're all going to be in physically different memory locations on the stack, and these counters are not going to be shared, and it will not appear to the cache hardware as if that there is false sharing. So it is very performant and cache friendly just by adding that local variable. That is all we have done. And then we keep updating this local variable, and finally we update the shared variable once. Why do we update the shared variable? Because each thread computes its local value. If we don't update the shared variable that is accessible to the main thread, this counter will be lost because it's a local variable for every thread. You can't access the counter outside. So we store the value of counter into the shared vector, so it is accessible in the main thread to do the accumulate. Yeah. Since we are updating this shared vector once, there is still some false sharing. That means we are not completely eliminating false sharing. We are reducing false sharing substantially, and consequently, this version of the solution is cache friendly and performs much better than the previous version. In the next part, you will be trying out these solutions in the lab and measuring the performance of these two different solutions, so you can see the impact that false sharing has on degrading performance, and see the solution that adding that simple variable will improve the performance of this reduction approach. Good luck.